Hi, today we're going to start chapter 3 with 3.1 derivatives of a function. We're going to talk about the definition of a derivative, different derivative notation, relationships of the graphs f and f prime, and really f double prime, and one-sided derivatives. Definition of a derivative will look very familiar. It's the same definition we had when we were trying to find rates of change, also known as the slope at a specific point. So when we were trying to find the slope of a curve at a specific point, we had the exact same definition, meaning all a derivative is the function of f's slope. So it's just the slope of whatever f is. So f prime is the slope function of f. Is another way you can think of it. So same definition, so it's stuff we've been using. So I'll do an example really. What is the derivative of f? Where f of x equals x squared plus 4. So same thing we've done from unit 2. Let's make this, we're going to do x plus h squared plus 4 minus x squared plus 4 all over h. We're going to find the limit of that as h goes to 0. Okay, so we're going to find the derivative. In other words, we're going to find the slope function of f. Okay, so same thing we've been doing. This is equal to the limit as h goes to 0 of x squared plus 2x h plus h squared plus 4 minus x squared minus 4 all over h. Here, my negative 4 and positive 4 cancel. My negative x squared and x squared cancel. I'm left with the limit as h goes to 0 of 2x h plus h squared all over h, which equals the limit as h goes to 0. If we factor out an h up top, we get h times 2x plus h all over h. Our h's cancel. I can now do the limit as h goes to 0 by substituting in the h, or the 0 for h, now that we don't have a 0 in the denominator. So this equals 2x. So f prime of x, the slope function of f, is equal to 2x. So this will tell us anywhere along the function f, like let's say if I was at 2 on the f function, the slope at that point 2 is going to be, if I just plug it into f prime, would be f prime of 2 equals 2 times 2, which is 4. So at an x value of 4, if I was to look at the graph of x squared plus 4, it would have a slope of 4 there. Okay, you try this, find f prime, that's just another way of saying the derivative of f. If f of x equals x cubed plus x, hit pause, go. Okay, so hopefully you did the same thing and you said that the limit as h goes to 0 of x plus h cubed plus x plus h minus x cubed plus x all over h, which is equal to the limit as h goes to 0. Use Pascal's triangle, we get 1x cubed plus 3x squared h plus 3x h cubed plus h cubed plus x plus h minus x cubed plus x all over h. Alright, and we can see the x cubes canceled. This should say minus right here. That's a minus. So that negative x cancels with this x. Okay, and now we can factor out an h from the numerator, which would give us h times 3x squared plus 3x h squared plus h. That should just be an h. This up here should be a squared. Sorry about that. So now it's h squared plus 1 all over h. My h is canceled. Now I can plug in the 0 for h because I don't have a denominator of 0, so that will cancel that. That will cancel that. And I'll be left with f prime of x equals 3x squared plus 1. So hopefully you got that. You had the harder one. I gave you the harder one. There you go. Happy birthday. Hope you enjoyed it. Don't say I never gave you anything. Moving on. Okay, using the alternate definition of a limit, you've seen this before again, using now specifically f at the point x equals a, and then finding the limit as x approaches a. So you're basically, doing the same thing. Instead of h, a distance away from x, approaching 0, now you're going from x to a, but then as x approaches a, basically does the same thing. So just a different way to look at it. So we'll just do a quick example using that form. So using the definition, we set this up as f of x minus f of 1, because we're going to say a is 1 here. We're going to find out specifically at a equals 1, what we're looking at here, all over x minus 1. So this would go to x squared plus 4. Oh, and this is the limit as a, sorry, not a, as x goes to 1. Same thing over here, limit as x goes to 1. Okay, so there's the f of x minus f of a is x squared, not x squared. It's not x anymore. A squared, which is 1 squared plus 4 all over x minus 1. So that simplifies to x squared minus 1 up top, because this 4 and that becomes a negative 4 cancels. all over x minus 1 below. Again, this is the limit as x goes to 1. We still can't plug that in because we still get a 0 in the denominator. So let's factor the numerator. That should go to x plus 1 times x minus 1 all over x minus 1. Those cancel. This was the limit as x goes to 1. So this equals, now I can plug that in and go one plus 1 is 2. So this is equal to 2 at an a value of 1. Okay, derivative notation. There's different ways you can write derivatives shorthand. Instead of writing derivative, you can write dy over dx, and you can say the second derivative is d squared y over dx squared. So that's the first derivative and the second derivative in the first notation. Okay, the notation another notation that's very frequently used is f prime of x, the first derivative, and f double prime of x is the second derivative. You can go third derivatives, fourth derivatives. Usually if you're using these, the f primes, if you go anything past 3 derivatives, it becomes f to the n of x. So if it was a fourth derivative, it would be f to the fourth of x is kind of how it would be written. So know that that is something that you might see. It doesn't keep on going with all those primes, or quotation marks, I guess they look like. Okay. Other ways you'll see them, df of dx, first derivative, or d squared f of dx squared, which is pretty much the same way as the next way it's written. It's just getting even more specific and saying this is f is in terms of x now. So same thing with these two, it's just being more specific. Okay, there are a couple more ways that you'll see them written maybe, but these are the most popular in the way that we'll use them in class for the most part. Let's talk about the relationship between f prime and f double prime. In other words, what's the relationship between the function f and its slope function, which is called f prime, and then what's the relationship between f prime and its slope function f double prime. Okay, well, let's take a look. If f is this cubic function, we can look specifically as we come up here. We can kind of look at that slope and what's happening to the slope. So we've got a positive slope here. If we were to try to estimate right at -2, okay, if I was looking at that slope, I'd say it probably goes from about here up to there if I was to draw a good tangent line there. Okay, that would be from about -2¼ over to the right to about, I'd say that's about -1¾ so that's a horizontal distance of 0.5, and it's going from -1 to 1. So the change in y over the change in x there, that would be let me see if I can even draw this little tangent line here. So I'm talking about that tangent line. Okay, I would say that it has a delta x and a delta y of, this is 2 and this is 1/2. So the slope there would be 2 over 1/2, which is equal to 4. If we look now, I'm going to erase. Well, maybe I can't erase. Oh well. If we look on the f prime function, look at 2, what the value is. The slope at an x value of 2, we said we estimated it to be about 4. Okay, on this f function. So right there at that -2, we said that we thought the slope was about 4. Well, look, if we look at the slope function right there it crosses at 4, at 2. Okay, if we come over to here, here's an easy slope to say. We know that that's a slope of 0. Well, if we come straight down, guess where it crosses? The x-axis, which is a value of 0, so the slope function matches there. As we keep coming across here, you can see here we've got a negative slope, and that's the steepest negative slope. Well, look on the slope function. That's as far negative as the slope function goes. That's as steep as that slope in the negative direction gets, and then it starts getting less steep, less steep, less steep until we get to a slope here on our f function of 0. We'll look right up above that. Here it crosses again that axis, and then as we go it starts getting steeper and steeper and steeper, and this graph gets more and more positive. Okay, so that's a little bit confusing. Let's look at how f prime looks compared to its slope function f double prime. So here we have a negative slope that's fairly steep, okay, but it gets less and less steep as we come till we finally hit 0. Okay, so here we have a negative slope that gets less and less and less until it finally hits a value of 0. Then our slope starts getting positive and it gets steeper and steeper and steeper as we go. Well, f double prime starts at 0, gets positive, and gets bigger and bigger positive as we go. Okay, so that's the relationship between f and its slope function f prime, and the relationship between f prime and its slope function f double prime. So you can kind of see when you take a second derivative, you're really just finding the slope of that first derivative. Okay, the slope function of that first derivative. Really quick, what do you think? Hit pause when you answer this. What do you think f prime prime prime, f triple prime of x, or the third derivative of f, would look like? In other words, what would the slope function of the f double prime look like? Hit pause, see if you can figure it out. Okay, for me, I would go, okay, this is a straight line. It has a constant slope. So from here up to here, that looks like it's going over 1 up 3, so that has a positive slope of 3. So the function f triple prime would be the graph here of f prime 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 of x equals 3. Okay, so that would be the graph of f triple prime. So if you got that, you are doing awesome. Go ahead and pat yourself on the back. Alright, this one's hard, but I have lots of faith in you. So I want to see if you can do a fairly good job. It doesn't have to be perfect, but do a fairly good job of taking this derivative function that's graphed. This is the graph of f prime. That's kind of not very clear there, so I'll write it off to the side. It says f prime of x. Okay. Try to go the other direction and graph the function of f. So what's graphed here is the slope function. So we'll talk about it for a second. Here at the very beginning, it has a slope of 8. Here it has a slope of 0. In other words, that's where you'll have some sort of maximum or minimum, a little local maximum or local minimum. Okay, down here you'll get as steep as the function will get. Alright, in the negative direction, and then it will come back up until it hits a slope of 0 again. Then it will go back down negative some more till it hits its maximum negative slope, and then it will go up to a slope of 0. Because then it switches to positive, we know that that's going to be another local minimum or maximum. I'll let you try to figure that out. And then we become more and more positive with the slope as we go. So go ahead and hit pause, see if you can draw what you think the graph of f looks like. give it a shot based off of this slope graph. Go. Hit pause. Okay, so if I was just doing a rough sketch, I would do something that would look like, okay, I've got a steep, so if I'm just going to draw right underneath it, I've got something like a, I don't really know where this axis is. Alright, so maybe I shouldn't draw that. Okay, so I've got this steep slope at first, but getting lower and lower until I hit the 0 value. Okay, so that should line up with, it didn't really line up very well, but that point should line up with that point. Okay, we'll call it point 1. Then it's going to go negative, negative, negative till it hits its steepest negative value, which should match there. So that's 2. Then it kind of gets less negative, but still negative till it goes to a slope of 0. So we'll say that's 3. Then it's going to go negative again until it hits its steepest point. That would be point, oh, that was 3. So we'll call this 4, steepest point. But then it gets less negative, okay, until it hits a slope of 0 again. That's the 5th point. Okay, and then it actually comes back up something like that. So we have our last point here, we'll call it 6 and 6. So that's kind of how I would try to draw this. Now if I look back, it says sketch the graph on the interval if f of 0 equals 0. So now I can kind of go back and draw my axis to say it'll look something like this, because that point now is at 0, 0. So I could draw it to look like that. Okay, let's see how I did compared to what the actual graph looks like. There's what the actual graph looks like. So it was okay, not bad. What I don't really like is this graph on here looks like, here it looks like it goes concave down a little, and here it looks like it goes concave up, and it does not do that. It actually doesn't go positive at all there, so that's the only thing I don't like about that graph right there. So I'm not saying mine's better, I'm just saying mine's better. What? Anyway, alright. One-sided derivatives, last topic we'll talk about here. So we're going to be looking at this point here where we have a left side function. Alright, this is a piecewise function. On the left side we have x squared plus 2x minus 1, and on the right side we have negative x squared plus 2x plus 1. So if I was trying to find the slope equation of this, you can hit pause and actually calculate this out if you want, but I know that the slope function, or f prime of x, is actually equal to 2x plus 2 on that first interval, and then negative 2x plus 2 on the second interval. So if I'm talking about at an x value of 1 there, it would be 2 times 1 plus 2. So my first, from the left side, the slope would be 2 plus 2 is 4. So if I look at that, the slope there, the tangent line's slope is 4. Okay, that looks like it would be pretty close to 4. And then if I went from the other side, I'm looking more at this. This looks like it's going to be pretty flat there, so it should be close to 0. Let's see. Negative 2 times 1 plus 2 is equal to 0. Okay? Like I said, if you don't know where this came from, use the definition of a derivative to find the derivative of both of these. They will be these functions. So I kind of cheated there and just used some prior knowledge that some of you might have. So if you do, awesome, good work. If not, we will have it all soon. But what this means is there is no derivative at f of 1. In order to have a derivative at f of 1, one of the rules says you have to have the derivative from the left be equal to the derivative from the right. Since the derivative from the left is equal to 4, and the derivative of the right from the right was equal to 0, there is no derivative. So that's kind of where we use one-sided derivatives. That wraps up the first lesson in Chapter 1. Hope you guys stayed awake, and we'll bring your questions to class. We'll go over them. See ya.